Okay, what's up everyone? Welcome back. Today we're talking a little bit about orthonormal bases. So first off, we're going to have to start talking about what it means to be an orthonormal list to make any sense of this. And then after we have that down, we'll prove a few facts about orthonormal lists, some nice inequalities, some nice statements about bases, and then we'll describe the Gram-Schmidt procedure, which is something that you might have seen before, but in the more specific context of Fn, where F is the reals or the complexes. That is, n copies of the reals or complexes. Okay. It turns out you can do the same trick in other places. We'll build up to it. First off, let's define orthonormal. So, orthonormal. We'll say that a list of vectors is an orthonormal list if each vector in the list has norm 1 and is orthogonal to all the other vectors in the list. Okay, so the idea of it is there's two parts. Ortho. This is the orthogonal bit. So it says that they're orthogonal, pairwise. Normal says that they are, you can think of it as normalized, i.e. norm 1. That is unit norm. They basically, if they're not norm 1, they've been shrunk to be norm 1. That's the idea of it. So, orthonormal, it's just a list E1 through EM of vectors such that the inner product of EJ with EK basically works like a Kronecker delta. That is, it's 1 if J is equal to K and 0 if J is not equal to K. Okay, so this gives us a whole lot of nice things. We can use this tool in a very good way. And notice, one thing that comes out of this is the normality condition. So, EJ, that's equal to 1, which is equal to the norm of EJ squared. And the only thing that you can square, the only real number you can square, the only positive real number, I should say. Sorry, I almost spoke too quick there. The only positive real number that you can square to get 1 is 1. So EJ has norm 1. Nice. Pretty cool. All right, so orthonormal. Hopefully not too crazy of a concept. Something probably you've seen before. We're just doing it abstractly for a vector space V with an inner product. All right, now here's a nice fact. If you have an orthonormal list of vectors in a vector space V, then the norm of a linear combination of those vectors squared is just the sum of the squared coefficients in that combination in modulus or absolute value, whether you're in the reals or the complexes. Okay, let's do a quick proof of this. So to do it, we'll have to use the Pythagorean theorem. So, which, recall, says, and let me zoom out a teeny tiny bit, give ourselves a little bit more room to write. That the norm of V plus W squared is equal to the norm of V squared plus the norm of W squared for VW orthogonal. We get the following. So here's the trick of it. Notice, since each vector is orthogonal to all of the other ones in the list, then we can write this. The norm of A1, E1 plus all the way down through AM, EM squared. Well, this is just the norm of A1, E1 squared plus the norm of A2, E2 plus all the way down through AM, EM squared, since the inner product of A1, E1 with A2, E2 plus all the way down through that, AM, EM. This guy, I will write this vertically here, which is maybe not ideal, but I'll do it anyway. This is just equal to A1, E1, maybe even let me break this up even further. Here, I'll just take the A1 out of everything, and then I'll get E1. Here, let me even write this a little bit nicer. I'll take the A1 out, and then I'll pull it out of everything else that I break up here, and then I'll get A2, E1, E2 plus A3, E1, E3, and so on, all the way down through AM, inner product E1, EM, which is just A1 times A2 times 0 plus all the way down through AM times 0, which is just 0. So here, let me make this into like a parenthetical right here. And say that that's why we're getting this. And then doing the exact same thing a whole bunch more times, just with A2 now and so on, we will just get norm of A1, E1 squared plus all the way down through AM, norm AM, EM squared. But now I just have to pull things out, and I'll get the modulus, or in the case of the reals, the absolute value of A1 squared norm E1 squared plus all the way down through modulus of AM squared norm EM squared. And since all of these guys have norm 1, I just get A1 squared plus all the way down through AM modulus squared. And hey, that's what we wanted to show, right? This little bit right here is what we got right at the end. Nice. Okay. So these guys are pretty easy to work with. Normally it's kind of hard to say anything about a sum of lists of vectors, especially about their norm, something like that, right? It could be almost anything. But when that list of vectors has a nice structure, that is, it's orthonormal, then you get a very nice way to write the norm of a linear combination of the vectors in that list. It is just the sum of, or is the, in particular, if you want to take the norm of this thing, you take a square root of this other side. It's the square root of the sum of the squared modulus of the coefficients. Nice. This gives us something pretty cool. Every orthonormal list of vectors is linearly independent. This is kind of wild because it might not seem immediately apparent. That is, it might seem like it's possible to get orthonormality without linear independence. After all, linear independence doesn't really have anything at all to do with an inner product, seemingly. And you could, have many different inner products on your space. So what the heck goes on here? How does being orthogonal and having norm 1 with respect to some particular inner product give you linear independence, which is a statement just independent of entirely, and it's kind of weird to use the word independent right there, but independent of the inner product. That is, it doesn't involve the inner product at all. It should hold no matter what the inner product is. So this is actually kind of a cool and strong result. Let's think about it. So let E1 through EM be an orthonormal, which I'll abbreviate by ON just to save us some writing, list in V. Let A1 through AM in F be a list of scalars such that A1, E1 plus ... all the way down through AM, EM is the 0 vector. Then, using the previous result, we have that 0, well, this is equal to the norm of A1, E1 plus ... plus AM, EM squared, certainly. Okay, but we know that that is equal to the modulus of a1 squared plus the modulus of a2 all the way down to the modulus of am squared. So a1 is equal all the way down through am is equal to 0. Oh. And e1 through em is linearly independent. Nice. Does everyone see why this means that all of the AIs are 0? Mostly because we're adding numbers, real numbers, that are at smallest 0. So you can't add a bunch of positive numbers together and get 0. You can only add a bunch of zeros together and get 0. Or add positive and negative numbers. But none of these are negative, so they all have to be 0. Nice. Okay, let's keep going and let's prove something called Bessel's inequality. Okay, here's what we're going to do with this. We're going to prove a bunch of facts. I'll show you. So, if we've got a list E1 through En that is a basis of V and is orthonormal as well, pairwise orthogonal, norm 1, that is, if it's an orthonormal basis of V and U and V are two vectors in V, then we have all of these statements. First off, for any vector V, you can write it as a linear combination of the elements of this basis, obviously, but the coefficients are just the inner products of V with the corresponding basis element. Ooh, that's nice. In particular, among other things, this says that the dual basis element corresponding to a basis element in an orthonormal basis, it is an inner product. Whoa. We'll talk about that more next time, but for the moment, just notice this looks like what the definition of a dual basis is doing, right? Like what's going on in a dual basis is you're getting coefficients. We're getting the coefficients here from inner products. Maybe this tells us something about how to represent things in the dual space using an inner product, and indeed we'll prove something along those lines. The second piece just follows pretty straightforwardly from this. It is the result from the last thing we proved, except now, instead of an inequality, we actually get an equality. It says that the norm of V squared is the sum of the squared moduli of the inner product of V with the corresponding elements of our orthonormal basis. And then finally, it says that the inner product of U and V is equal to the sum of the inner product of U with each element in our orthonormal basis times the conjugate of the inner product of V with the element of the orthonormal basis. So the thing in the second argument, you have to conjugate the inner product there. All right, let's prove it. You'll see the last one much better once we get to it. It won't seem nearly as strange once we do the proofs of the first couple. So for part A, since E1 through En is an orthonormal basis, ONB, there exist scalars. Let me make this a little more zoomed out so I have some room. A1 through AN in the field, that's an A, such that V is equal to A1 E1 plus ... all the way down through AN EN. But notice the following. V's inner product with EK then becomes equal to, well, it's the inner product of A1 E1 plus ... all the way down through AN EN EK. Okay, but I can split this up. I'll get A1 inner product E1 EK plus ... all the way down to the last one, AN inner product EN EK. Oh, wait a second. All of these are 0 except for the kth one, in which case I get EK next to AK. The rest of them are 0 by orthogonality. That is, EI EJ inner product is equal to 1 if I equals j and 0 if not. So the only one here that's not 0 is this one. And in particular, this just gives you ak. Oh. Hence, v is equal to v e1 plus dot 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 all the way down through v en, inner product en. Bada boom. Look at that. Kind of nice, yeah? So we've got our first result. Check. Second one, not too bad. Using a, the norm of v squared is equal to, well, just think about it. What is it going on here? All we got is we're going to take this long thing and inner product it with itself. Or, even easier, if we take the very first theorem of the section, we can just use this. Oh, wait. The norm squared of a linear combination of an orthonormal list is just the sum of the squared moduli of the coefficients in that linear combination. Bringing it back over here, we just get VE1 in modulus all the way down through VEN, inner product in modulus squared, via the first theorem of this section. Oh, that's not bad at all. And then finally, for C, we'll have to do this. We'll have to break this thing down, which is a little bit of work. Okay, so all we're going to do is we're going to break down U and V in the way prescribed by A. We get the following. So we've got a U and a V. Okay, inner product of U with V. Well, this is just the inner product of how can we write U1, or how can we write U? Well, I'll write U out as the inner product of U with E1 plus dot 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 all the way down through the inner product of U with En. And then for V, I'll just do the same thing. Inner product of V with E1 plus dot 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 all the way down through inner product of V with En. Now I just have to break all of this down. Oof, what a long inner product to break down. Let's just do it. All right, so first off, we'll break it along this sum right here. I will use some judicious copy pasting. Here, actually, make it even easier. Okay, now let me get to writing a little bit. Okay, and first off, I will have let me even just do this here. Oh, I'm getting a little bit confused. Okay. Let's see. There we go. Oh, okay, here. Let me do this. All right, 1 second, everybody. Sorry about that. Sometimes it is slightly easier to use computers, and sometimes it is slightly harder. Now, I will just be able to do this and save us some time in writing. Sorry, here. It's probably actually made it seem kind of more confusing, whatever's going on. Let me do this. Some technical things going on behind the scenes right there. All right, so all I'm saying is, hey, let's take and break across the sum from the first piece. Okay, now I can take this and I can move it and I can go dot, dot, dot and say some stuff. Now, I may have to do a very slight bit more moving. I thought this would make our lives slightly easier, but it actually made it take a little bit longer to write this. Sorry, guys. All right. Back in this one. Okay, there we go. And now I will not do that again because that took too long to do. Plus ... And now I'll do at the very end, I'll just switch this to UNEN. That is, I just broke everything up across the sum in the first argument, right? So here, I could take this first piece, inner product with the rest of it in the second argument, plus, so that's what I have right here, and then so on all the way down through the last piece, inner product with that bit. Now, if I do this, this is going to be a little bit annoying to write it all out. I will just get UE1 inner product with E1, comma, the rest of everything right here. So let me just start writing it out. I'm going to split it across its sum as well. VE1, E1, and I will put a parenthesis here, plus ... all the way down through E1, VEN, EN, okay. And then I'll go plus ... all the way down through the end with my UEN. I'm going to do the exact same thing. Inner product of EN with VE1, E1 plus ... all the way down to the very end. Inner product of EN with VEN inner product times EN. Bam. Wow, that took a long time. Now all I have to do is pull out some scalings. So these guys, I'm pulling them out of the second argument, so I have to conjugate them. So I have a U, E1, inner product, and then I will get a V, E1 conjugate times inner product of E1, E1, plus ... all the way down to the very end. Now I have my VEN conjugate, inner product of E1 with EN. And the same going all the way down. And I'll have my UEN inner product, and I'll do the same thing on the last bit. Oh, tedious. VE1 inner product conjugate, inner product of EN with E1, plus ... all the way down to the very end, inner product of VEN conjugate, inner product of EN with EN. And all of that is still in parentheses. Wow, super long. But notice it's going to get way easier right now because we have a lot of inner products of the orthonormal basis elements with each other, and most of them do not have the same index. That is what I'll end up getting from this first bit, is I'll have my UE1 inner product that's just still sticking around, and then inside the parentheses here, everything is 0 except for this first term. So I have my VE1 inner product conjugate times inner product of E1, E1, but that's just 1. So I'm not even going to write it if that's all right. And the rest of it is just zeros. And so I can go plus ... all the way down to the end and do the exact same thing with each one and get VEN conjugate there. And hey, wait a second. Have I written this all good so far? Yep, this looks right, because up here, we said that the inner product of U with V is equal to the inner product of U with E1 times the conjugate of the inner product of V with E1, plus all the way down through the same thing up to EN. Do we have that? Inner product of U with V is the inner product of U with E1 times the inner product of V with E1 conjugate, added up all the way the same way down to the inner product of U with EN times the inner product of V with EN conjugate. So we are done. Nice. Now, the next little bit here, the thing that we're going to go to after having proved this result, is as follows. It's the Gram-Schmidt procedure, and what I want to do is think about the following idea. If we have a basis of an inner product space V then how can we make that basis orthogonal in the easiest way? That is, let's draw the picture. So here's kind of the picture of it. Maybe we're sitting in like R2, and here's V1, and here's like some V2. Okay, suppose this is the basis for R2 here that we're going to deal with. All right, let me draw a nice couple of axes or something like that to make everything look smooth. Okay, here's the trick that we're going to employ. The essential kind of idea of all of it is that what we'll do is we'll say, hey, V1 right here, it's fine, basically. We don't have to do anything too fancy to V1. We can just leave it alone. But V2 is not really at a right angle to V1, right? However, if we break V2 down, notice that there's a piece of V2 that lies on the subspace spanned by V1. That is, if I just kind of continue this line out, right? I can see pretty easily, and maybe I should have drawn V2 shorter. Actually, if you're all right with it, here, let me do this really fast. Let me make this into V2 and this into V1, just to make our lives easier. Okay, if I do that, V1's fine, but V2 is not at a right angle to V1. Now, if I look at what's going on here, though, I can say, hey, relative to V1, there's a little chunk of V2 that is orthogonal to V1. Not all of it. There's a piece here that is not. So I've got this chunk right here, and I've got this chunk right here. So let's call this like U and W. All right, notice V2 is equal to U plus W, and W and V1 are orthogonal. So just take V2 and remove the part of it that isn't orthogonal to V1. Then normalize, i.e., replace V1 with V1 over norm V1 and W with W over norm W. Then I've got two vectors that are orthogonal. The first one is just a scalar multiple of V1. The second one is a scalar multiple of the chunk of V2 that is orthogonal to V1. This is the idea of the Gram-Schmidt process. We just do it a ton of different times, a ton of times in a row. So let's get on to it. Let's describe the Gram-Schmidt process. Let's prove that it actually works to do what we want. Okay, so the Gram-Schmidt procedure. Let's do it. The Gram-Schmidt procedure is kind of fun. So the idea of the Gram-Schmidt procedure is as follows. If you've got a linearly independent list of vectors v1 through vm in a vector space V with an inner product, so an inner product space, I suppose, the idea is that we'll generate these vectors, which we'll call f1 through fm, and we'll define them inductively so that f1 is equal to v1, and for k larger than 1, we have fk is equal to vk minus the sum of the inner products of vk with f1 divided by the norm of f1 squared, scaling f1, all the way down through the same thing up through k minus 1. Okay, Then what we'll do is we'll take our fk's and we'll normalize them. That is, we'll divide them by their length, so they have length 1. The claim here is that E1 through EM, this thing we get from taking our f's and normalizing them, is an orthonormal list of vectors that has the same span as the original vectors for each k. That is, the span of E1 through EK is the same as the span of V1 through VK for k equals 1 all the way up to m. All right, so let's do the proof of this. Now, it's not too bad. The gist of it is basically the picture we just drew. So the idea is, hey, we'll take f to be the previous vector, and then we'll subtract the chunk of it that is not orthogonal to f1, and we'll subtract the chunk of it that's not orthogonal to f2, and so on, all the way up to the chunk that is not orthogonal to the k-1th f. Then we'll just have the piece of vk that is orthogonal to all of the previous f's. After that, all we have to do once we've generated all of our f's is normalize them. So we'll pull it together. Okay, so the trick here, I don't want to do more than just kind of a sketch here, since this is a pretty long proof to do in its full formality. The idea basically is to do induction on k. If k equals 1, then f1 equals v1, and E1 is f1 over norm f1, which is just equal to v1 over norm v1. So E1 has norm of, I'll put this in bars, v1 over norm v1, but I can just pull out that norm v1, and then I get, well, I guess I should be very careful and say this is norm of 1 over norm v1 in absolute value, but since that's positive, I just get that this is equal to 1. Yeah? Okay. And obviously, and I would say pretty straightforwardly, E1 is in the span of V1. So span E1 equals span V1, where perhaps I should specify that this is not 0. So that span is, not just the 0 vector. Okay, so we've got everything we need. And we don't even have to worry about the orthonormality piece right there, since any list of length 1 is automatically orthonormal, right? Okay. Now, the idea from here is to show that everything works up to k-1. So the idea is that, i.e., that E1 through ek-1 is an orthonormal list such that the span of V1 through I should say k-1 here, I guess, is equal to the span of E1 through ek-1. Okay, then we just want to do the same thing then build ek and show everything is still good. This is not too bad. So fk is just equal to, well, all we have to do is write it out. Fk is still just equal to Let me scroll up actually a little bit to make this easy to see. It's this terrible looking formula right here. Let me just take this and even go Control C, Control V, and move it on down right here. Yeah? Okay. So FK is this, and EK is equal to FK over norm FK. So, watch this. EK, EJ's inner product, well, just write out which each of them is. This is FK over norm FK, inner product with FJ over norm FJ, right? So this is the inner product of, let me even write this first bit out front. I get 1 over norm FK times the conjugate of 1 over norm FJ, but norm FJ is real, so it's just equal to 1 over norm FJ. Okay, cool, since norms are always real numbers, not complex numbers. And then I just have the inner product of FK with FJ. Yeah? All I have to do now is write out what FK is. Yeah? So I'll just write out what FK is yet again. Let me even do this here. Just for convenience, maybe not so convenient, I suppose, but I'll take this piece here and I'll move it over. Then, going back down here, I will take this piece and I will move it over as well, just a little bit. And I'm going to get rid of all of that annoying, not the same color piece really fast. Okay, there we go. Nice. Okay. And so I have still 1 over norm FK, norm FJ, inner product. This is what FK is. It's this long thing. And then I have an FJ, where here, J is less than K. So just expand it out. I still have my 1 over norm FK, norm FJ, and then I just break this apart. VK, FJ, okay, and I'm going to put a big parenthesis here so I don't have to keep rewriting that piece, minus, and I'll pull this part out front, VK, F1, inner product over norm F1 squared, inner product F1, FJ, minus dot, 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 all the way down to minus. Then I just take that piece out yet again, VK, FK minus 1, inner product over norm FK minus 1 squared. And then this is all multiplied by the inner product of FK minus 1 with FJ. And that's still all in parentheses. Notice all of these F guys, yeah, most of these inner products will go away. Why? Because our our E1 through EK minus 1 list is orthonormal. Certainly our F1 through FK minus 1 list is orthogonal. It's just not normalized. It's E1 through EK minus 1, but just with each vector potentially stretched out a little bit. So all I end up getting right here is 1 over norm FK, norm FJ. Nice. And then this long thing right here will just turn into a VK FJ minus the one place where J is equal to the corresponding piece right there. So I'll get a VK FJ over norm FJ squared, and then I'll get an FJ FJ, since the rest of it is all zeros. That is, if this first number is not equal to j, then that inner product is 0, and I don't have to care about the rest of what's next to it. But hey, wouldn't you know it, now, what is norm fj squared? Well, it's the inner product of fj with itself. So this and this guy cancel out, and I get vk fj minus vk inner product with fj. So I get 1 over norm fk, norm fj out front. It's this little factor right here. But then I get vk fj minus vk fj, and that's just 0. Hey, wouldn't you know it, you've still got orthogonality, and then you're good to go. I guess I should say that then we should show the span bit. Which is not bad. So maybe you don't believe me there. But if you want to do the span bit, that is to show that the span of v1 through vk minus, or span of v1 through vk is equal to the span of e1 through ek, all you got to do is note the span of v1 through vk minus 1 is equal to the span of e1 through ek minus 1. So if you just throw on that vk to the span of v1 through vk minus 1 and turn it into the span of v1 through vk, all we have to do is show that vk can be written as a linear combination of the span of e1 through ek. If you don't believe that, I claim that you can see most of this just from looking at the length of the list. That is, all you have to do is just, well, sorry, maybe I'm being silly, is just look at the fact that, or I'm not being silly, but I'm being pedantic. All you have to do is look at the fact that fk is vk minus a bunch of stuff. Here, let me even zoom in a little bit closer so this is super clear. All you have to do is look at the fact that fk is equal to vk and then minus a bunch of stuff in terms of f1 through fk minus 1. Just manipulate this, and you get that vk is equal to, I will say, this stuff right there, minus that stuff maybe, minus that stuff. Let me write that a little bit nicer. Minus, in parentheses, that stuff. Okay, so I've got all this, I subtract it over to the other side, right? It's minus that whole thing, turns all those minus signs into pluses, plus fk. And vk is then equal to, well, all of these things are in terms of fk's. So it's a k. All of these things are in terms of fk's, and fk's are just, or f1 through fk, right? fi's, let's call them. And all of these fi's are just scalar multiples of the ei's, right? The only difference between fi and ei is whether or not you've divided by the length of fi. So we're good to go. Okay, nice. Not too bad. So that's the idea of the Gram-Schmidt process. It says, hey, you can take a linearly independent list of vectors and then start with one of them, normalize it, cool. Then take the next one and pull off the piece that isn't orthogonal to the previous one. You can keep going down the line and take the next vector, pull off the piece that isn't orthogonal to the first vector, the second vector, and so on, up to the index that you're at in the list. Then when you've done that, all you have to do is normalize, and bada boom. Nothing to it. So let's go a little bit further and talk about some consequences of the Gram-Schmidt procedure and see what we can do with this. Okay, first consequence. Every finite dimensional inner product space has an orthonormal basis. Proof. Super easy and fast. Take a basis and apply the Gram-Schmidt process. That's it. All you have to do is take a basis, apply the Gram-Schmidt process. We know that you end up with something that spans the same space, and we know that every orthonormal list of vectors is linearly independent, and so bada boom, you got an orthonormal list, or a linearly independent list of vectors that spans the space and is the length of a basis, so it's an orthonormal basis. All right, here's another one. Every orthonormal list extends to an orthonormal basis. So if you take a finite dimensional vector space, our claim is that every orthonormal list of vectors in V can be extended to an orthonormal basis of V. Take the orthonormal list, which is linearly independent. We showed that every orthonormal list is linearly independent, and extend to a basis. Then apply Gram-Schmidt to this basis. Only the elements added in the extension are changed, since the first part is already orthonormal. Ha! Okay, that's super easy. And this gives us something that maybe it seems like it's a little bit out of left field. It says, hey, if you have an operator T on a finite dimensional vector space, then T has an upper triangular matrix with respect to some orthonormal basis of V, if and only if the minimal polynomial of T is z minus lambda 1 product all the way down through z minus lambda m for some lambda 1 through lambda m in the field. Okay, we'll have to go back to something we've said before, but this isn't too bad. So here's the idea. This is the same condition as I'll say as what we had for getting an upper triangular matrix of T with a regular basis. So just use the fact that we can orthonormalize this basis with Gram-Schmidt, and we are done. That is, this was the same result we had before. We said, hey, T is an upper triangular matrix with respect to some basis of V, if and only if the minimal polynomial of T is of this form. But all we have to do is take that basis and orthonormalize it. Bam! Now we still got an upper triangular matrix. All right, sweet. If you don't believe that you still have an upper triangular matrix, all you need to note is that the span of V1 through Vk is still the span of E1 through Ek when you orthonormalize the list V1 through Vm. That is, the span of the first k elements of your list is the same as the span of the first k elements of your orthonormalized version of your list. All right. Maybe I should say that, using the span of that. That says it. And this gives us something that is known as Schur's theorem. It is kind of an obvious fact, just basically another way of saying the thing above it. It says that, hey, every operator on a finite dimensional complex inner product space has an upper triangular matrix with respect to some orthonormal basis. That is, over a complex vector space, the minimal polynomial of T is always of this form. So T always has an upper triangular matrix with respect to some orthonormal basis. Oh man, that's nice. These are some quick consequences, nothing too much. Next time we'll really get into it. We'll talk about a lot more, and we'll get into how inner products interact with the dual space of a vector space. So I'll see you then. Have a good one.